Okay, welcome to today's lecture, which will be about modeling, and in particular, modeling using data types. So in the last lecture, we saw examples of data types, such as integers, floats, doubles, lists, the kind of things that you would see in many languages. But when it comes to modeling in programming, the ability to create your own data types is important. By creating good representations of the data we want to represent, by creating good models of what we want to program with, then programming becomes a lot easier. So in this lecture, we will talk about the main mechanism in Haskell for defining your own data types. And we're going to do this through one simple example, and it's the example of cards in a card game. Okay, so general motivation for being able to model, I think you by now all understand the importance of modeling and why we don't want to use basic primitive operations, primitive representations like computer numbers as our only tool for modeling things. So let's turn to the game of cards. Of the Western variety, which involves a number of different components, the first of which is the so-called suit, which is one of these four elements: a spade, a heart, a diamond, or a club. And this can be very easily modeled as an enumeration type, something you would be familiar with from Java, I presume. An enumeration type of this kind in Haskell would be modeled in the following way. The keyword data introduces the fact that we're defining a new data type, and this is the name of the new data type. It's a suit, and there are four different kinds of value in this data type, and these are simply enumerated, listed, and separated by the vertical bar character. So this is introducing a new data type with four new values. You will notice, just like the name of the type, the names of the constructors of this type, the values in this type, also begin with a capital letter. That's significant. Okay, so let me just go back to our live version of this. So there we have our new type. Let me just make sure I can compile it. So I can ask what does the interpreter think a suit is, and it just tells me, well, it's just what you defined and where it's defined. I can, for example, ask what the type of spades is, and of course it's a suit. Can I actually do anything else with them? Can I, for example, do that? It turns out we can't spell it right, but if we manage to spell it right, we still have a problem. And the problem is that when we introduce a new data type, we need to tell Haskell how the data type should be printed. When the interpreter gets a value of a data type, it converts that value to a string to display on the screen, if it knows how to do it. It doesn't always know how to do it. Some values we typically don't want to normally print. So what would be the example of a value that we don't normally want to print? Well, a function. In a functional language, a function is a first-class value. We can pass it around, we can put it inside data structures, we can take it out of data structures and use it, but it's not something we typically want to print out. We could print the name of the function, but is that really what the function is? Is the function a name? Well, the function is a mathematical object, maps inputs to outputs. So, in fact, if we tried, for example, to print a function, do you remember we had the function, what primitive functions have we seen so far? we had something called abs. It has a complicated type because there's lots of different types of numbers. Actually, it's not that bad. It just takes any number. If you give it a number, it gives you back a number, as long as it's something in the num class. So you know abs. What happens if I try and just compute abs? Well, we get a similar kind of error messages. We get an error arising from trying to print it out. So there's no way of printing a function. Well, we don't really want to print functions. We want to use them eventually. The same goes for suit here. The system doesn't know how we want to represent these on the screen. So we have to tell it how to do that. Now in this case, as in many other cases, we don't really want to do anything fancy. We would be perfectly happy if when we type spades, then the word spades gets printed on the screen. And we can tell it to do that by the following addition to the data type declaration. We should tell it to derive the functions for printing out things. So the functions for printing out things and similar things live in a specification, an interface called a class, and that class is called show. So it's saying derive the functions automatically in this interface. Let me just see what that interface is. Give me information about show, prepared for a lot of stuff to be printed, because there are a lot of instances of show. There are a lot of things that can be shown on the screen. But here's the important bit. The interface to the class show contains one very crucial function that we need, that the interpreter needs, and that is a function which converts one of those things into a string. So by telling it to derive this automatically, we're telling it to automatically create this crucial function. Okay. Now, this deriving is not magic. It doesn't know how to derive functions for arbitrary classes, arbitrary signatures of this kind. There is a certain collection of predefined classes where Haskell can automatically create appropriate functions. And show is one of those. We'll see a few more during today's lecture. So now, having added a show, now we have the ability to print out values. So, for example, clubs will indeed return clubs. We can put that inside things, and of course it will do things with it. Okay, that's not very exciting on its own. Let's define at least one function for this thing. Let's define the function which gives us the color of a suit. So this could be a function which maps a suit to something representing the color. What could we use for that? We could use a string, right? So we could map to a color to a string. But we could do a little bit better than that. We could give a little bit more precise modeling. We could define a new type. Also an enumeration type. It has two values. The color is either red or black. So we could define then the function. Let's derive show as well, so we can print them out. Otherwise, when we try and use the function, we won't be able to display the result. So a color will map a suit to a color. So how do we define this thing? What is our main weapon for defining the function color?
Pattern matching.
It's pattern matching. Pattern matching is our primary tool. The color of spades is black. The color of clubs is also black. The color of anything else for a suit S is going to be red. Okay? Just compile that, make sure it works. Color of hearts is indeed red. Okay? Now, just a little note about pattern matching and style. You notice that I called the suit S here. That's fine. But I didn't actually need S. I don't use S in the right-hand side. Now, there is a special pattern to use when that's the case that communicates a little bit more information, communicates your intention more clearly. And that's the so-called don't care pattern. And it's the underscore character. So the underscore character basically says it can be anything you like, and what's more, I'm not going to use it. So the underscore character is a pattern, can't be used in the right-hand side of a definition, and it clearly makes it clear that A, you don't care, and B, you're not going to use it in the result either. Okay, so the definitions are equivalent, but this is gives a little bit more information. Yeah, question.
Does this have any implications for like memory allocation?
Does it have any implication for memory allocation? That's an interesting question. I think the answer is no, actually. Okay, I guess it's possible that the compiler could statically take advantage of the fact that this is not used in the body, but it has to check that anyway. So the compiler could find that information out for itself. So it's hard.
That's not really an observation.
No, it's not an optimization. No, we let the compiler do the optimizations for the most part. So this is really just about communication of the intention. So we're using the Haskell interpreter here, which doesn't actually do a lot of optimization. But there is also a full-blown compiler. And the full-blown compiler does a huge amount of optimization. And Haskell is very... the Haskell compiler does an enormous amount of optimization. There are hundreds of different flags for getting combinations of optimizations. So all those kind of small stuff, you can certainly expect the compiler to do for you. So we're not really focusing on that aspect. Any other questions? Okay. All right, so here's the next thing that we're likely to want as part of modeling playing cards. A playing card has a suit, and the suit has a color, and it also has a rank: ace, king, queen, jack, plus a whole bunch of other things. So this is a partial definition. This doesn't cover everything that we want. We need to extend this with a bit more. This is missing the numeric cards. Okay, so we can add an extra item to our enumeration here to represent a numeric card. But we haven't got enough information there. We actually want to model not only the fact that it's a numeric card, but what the value of the numeric card is. Okay, so this needs to contain some information. The way that we can do that is that this particular constructor can actually contain more information. We can model, so let's model the rank of a numeric card by a small integer, an int. Now this is not a perfect model because it means that we can model a numeric card of value 17. So you can have the 17 of hearts. It's not ideal modeling. What you would actually like is a model which restricts the range to being in the range 2 to 10. Haskell doesn't have numeric range types. One of the reasons for that is that most of the types that we're using here are statically checked. They're not checked at runtime. And so that means that range types would be very difficult to handle, or much more difficult to handle at runtime. So Haskell doesn't try to do that. So some programming languages have very precise range types, such as the programming language Ada, used widely in safety critical systems, in particular aeronautics. That gives you the opportunity to model ranges of values very precisely, but there's a heavy runtime overhead associated with that. Haskell doesn't have that opportunity, so here I've made a trade-off. To keep it simple, I've just used int. But the main message of this is that a constructor, all of these can be thought of as constructors, this can be a constructor that has an argument. So let's also derive show for that. So we can have a numeric 6 is a perfectly good value of this type. So if we ask, give me information about a jack, it knows that it's defined in this data type. It's just not sure what it's going to tell me if I ask it about numeric. It just tells you where it's defined. What is the type of jack? Anybody? Type of jack is rank. What's the type of numeric? Rank? Maybe? It's a function. It's a function from int to rank. So if I apply numeric to an int, I get back a rank. So it's a constructor function, and it has an argument which is an int. Okay? Any more questions about that? Okay, let me pop back to the slides for a minute. The slides basically cover what I've talked about here, so if you want another view on the world, please look at the slides. So here we have a function called rank beats, and it's a function which will determine when one rank, first rank, is bigger than the second rank. Okay, so an ace is bigger than a king is bigger than a queen is not bigger than another queen, a numeric card, a numeric 7 is bigger than a numeric 5, and so on. Okay, so rank beats is a function that determines whether one rank beats another. So the slides give a definition purely based on pattern matching. It basically starts by saying an ace can't be beaten. So if you compare anything with an ace, then the answer is false. But an ace will beat anything else after this case has not matched, and so on. So you end up with a long definition of enumerating all the cases, starting with the biggest down to the smaller ones. And then finally we need to add the case for the numeric. So how do we do that? Well, again, we use pattern matching. We use pattern matching to identify the numbers inside the numeric type. So this numeric value beats this numeric value precisely when the value m is bigger than the value n. Okay? Bit of a rather big and hairy beast, but it looks reasonably logical, I hope. Let me just show you a different way to define that, which is actually much simpler. One of the classes that we can define is a class called ORD. What are the functions in this class? Let me just scroll back out. There are lots of instances of ORD. It's the class of ordering relations that contain these ordering functions. Okay? So if you have all of these operations, then you can be a member of the ORD class. Now, you also need to be a member of the EQ class. What's the EQ class? Again, I have to scroll back up to get the definition. The EQ class is a simpler class which basically has equality and inequality operations. Okay. Now, it turns out that these are both cases, EQ and ORD, which can be derived automatically. And if we want, so we can add more deriving things here. We have to put it in brackets if we want more than one. We can derive the equality function, and we can derive ORD. Now, equality, how it works, should be fairly obvious. A jack will be equal to a jack, a queen will be equal to a queen, a numeric will be equal to another numeric if the int inside it is equal to the other int. Okay? So equality is obvious how to derive equality, but it's actually not so difficult to derive an ordering relation either. What happens is you take them in the order in which they appear, so that an ace will be bigger than anything else to the left, king will be bigger than a queen, and so on, and a jack will be bigger than a numeric. And then if you want to compare two numerics, you go down inside and compare the ints inside. So this is a routine that can be automated, and it's automated as part of Haskell, so you can derive all the ordering relations automatically. Yes?
For example, if instead of int in numeric constructor, we will have something that are not inequality class.
Yes, so then it wouldn't work. So if we were to, for example, define a data value is 2, 3, and so on. If we wanted to model more precisely, we could do it this way. I mean, it'd be rather awkward. We would have to not only derive show, but also EQ and ORD for this guy in order for it to work on this guy. Yeah, that's right. So that the process that Haskell uses for building the ordering relation for these things is itself recursive, you might say. We're not going to do it that way, but we could do. Any questions? Okay, so if we do that, then the definition of rank beats becomes quite easy. So there's a longhand definition in the lecture notes. The shorthand definition, when one rank R1 beats another rank R2, is now, given that we've derived the ORD relation, it should be that R1 is bigger than R2, according to the derived ordering relation. Okay? In fact, there's another way we could have written this. We could have written rank beats is equal to the ordering function. I would give the same definition. I'm just saying this function, what is the definition of this function? Oh, it's the definition of this function. Okay. Any questions about that? Okay, now this definition is fairly straightforward, but we might still want to test it. In particular, if we have the definition from the lecture notes, it's a fiddly definition, not deep, but it's messy. Lots of cases. Did you forget a case? Did you get the cases in the wrong order? It's the kind of thing that would be quite useful to test. So if we wanted to test it, we might come up with a test for this function, R1, R2. So what would be a good test? Well, what are the basic properties that you expect for this? You might expect that either one rank beats another, or the other one, rank 1 beats rank 2, or rank 2 beats rank 1. Sound about right? Almost.
They're equal.
Or they're equal. So either they're equal, or rank 1 beats rank 2, or rank 2 beats rank 1. Okay? That's a reasonable property. If that fails, then we certainly know there's something wrong. So that's one example of a property we might write. So we might rank 1 equals rank 2, or rank 1 rank beats rank 2. So rank beats R1, R2, or the converse. Now, I just thought it might be actually nice to show you a little bit of an alternative bit of syntax. With these binary relations that we're defining, sometimes you forget which order they sort of are supposed to be used in. Which one is supposed to be which, right? These are definitions which actually are much easier to read in a sense when they're written in infix syntax. If I say rank 1 beats rank 2, I'm saying the word beats between the two subjects. It's much easier to understand than if I say beats rank 1 rank 2. I mean, it sounds like I'm speaking like Yoda if I do that. You can use any function as an infix operator if you put it inside back quotes. So that's quite nice for readability. So what I can do is I can use it as an operator, providing that I stick these little backticks around it. Okay? So R1 rank beats R2. Now we can read it as we intended it to be. So why not? Let's just do that. And let's finish the definition on the next line with R2 rank beats R1. So one of those three things must be true. Okay? Anybody see an obvious improvement to that definition?
The two uses or operators.
Yeah, so not a stylistic one, a logical improvement. Making a better property, a sharper property. Some properties are stronger than others. We want the strongest property we can think of to give us the most vigorous test.
So in this case, they could all three of them be true.
Exactly. We could have a trivial operation that always says true, and this would be a perfectly good test. So actually, of these three OR operations, exactly one of them should be true, right? Shouldn't be equal and one beats the other. So exactly one should be true. So what's the operator we need for that?
Exclusive OR.
Exclusive OR. Okay, exclusive OR. Question then, do we have exclusive OR? And if we do, how do we find it? Well, there is a nice way of there's a nice way of browsing the available functions in Haskell. Sometimes they need to be imported from a particular module. Sometimes they're already there for us. But the main thing is, how do we find them? Well, one nice thing about Haskell is this very strong type system that we have. We can use the type system as a way of searching for functions that we want. It's a bit like when you solved the high school physics problems involving velocity, acceleration, speed. You had a bunch of formulas in your book, and then you know this, this, and this. So I need a formula that has this, this, and this, and gives me this answer. You look it up. You match the things you know with what you want, and you find the formula that works. You don't have to understand anything. You put in the numbers, and out comes the right answer. My son's doing this at school, so I see how it works. You can do something somewhat similar in Haskell. Often, if you find a function with the right type, surprisingly enough, it does the right thing. So if we have a way of searching using types, then that would be cool. So you've heard of Google, good way of searching for things. There's another search engine called Hoogle. And it's a search engine which knows about and understands types, also understands when types are not exactly what you want, but similar. For example, if you maybe swap the arguments to a function, or maybe it's a more general type and you want something a bit more specific, it's good enough, it'll do the job. So let me just show you what that looks like. It's called Hoogle. There it is. It's under haskell.org. And you can search actually for names of things. So I could search for abs, just like you would in a normal search, and it will tell me various things involving abs. But I think more fun and more interesting is when you search using a type. So exclusive OR, XOR, if we had such a thing, it would take a Boolean first argument, a Boolean second argument, and give us a Boolean result. So we can ask it, what do you know about that has this type? And what do we see? We see the guys we've seen already, namely and OR. But we actually don't see here anything else that's really useful. These are very general types, A, B, A. I mean, that's much more general than we want. We want something really is that pretty much only works with bool. And the only things that only work with bool of this type are and OR. And they're in the prelude, as we've already seen. Okay? So actually, we don't have an XOR function. So what do? Well, we can define our own. And for the sake of the exercise, let's define it as an operator. And instead of defining it using and OR and negation, we'll define it using just directly using pattern matching. Okay. So what does XOR look like? If you have a true, let's find a nice symbol for XOR. It would be something like a plus in brackets. That looks kind of cool. If you have a true and a false, that should give me true. If we have a false and a true, that should also give true. And if we have anything else, anything XOR anything else, there's only 2 more cases actually, that will give us false. So there's an example of a signature for the XOR function. So now what we'd like to do is actually use XOR instead of OR. Well, let's just compile what we have first before we use it. Okay, that looks good. Let's change these ORs to XORs. Okay, something's gone wrong. Anybody got any idea what might have gone wrong? It's all got terribly confused. Well, in order for this to actually parse correctly, we need to know about the operator precedence. So when I had an OR in here, the precedence worked fine. So that this was a higher precedence operator than OR, and so I didn't need to put brackets around this expression. And this was obviously also a higher precedence operator than OR. So I need a way of actually setting the precedence of the operator. So what is the precedence and how is it set? Well, if we ask about, let's say we want XOR to have the same precedence as ordinary OR. I don't know if that's a good idea or not, but let's just say there's probably a sensible choice, but let's just take it, let's make it the same precedence as regular OR. So we can ask about what's the precedence of regular OR. If we want to ask about it as a function, we always put it in brackets. It says it's defined in somewhere deep in the bowels of GHC, and it has this declaration. It has a precedence level of 2. So it has quite low precedence. Let's compare that with equality. If we ask for equals, somewhere it should give us, yeah, there it is. It has precedence 4, it has a higher precedence. That's why we didn't need brackets. So actually it turns out that this is exactly the syntax we need for the declaration. We can declare a fixity. This is not terribly important. You're probably not going to use this, but I thought it would be fun to show anyway. It's not the most crucial thing. So now we can compile and presumably we can run, but we actually can't run yet. And the reason for that is that quick check, if we want to do quick check on this property, doesn't actually know how to generate random ranks. We'll actually have to tell it how to do that. We'll come to that later. Okay, that was a little diversion, a little exercise in pattern matching, a little bit to understand a bit more about operators and operator precedence, how we can actually even declare that. Not something I expect you'll use too often. Yeah, question?
We had an infix R2 for OR and infix 4 for equals. Does this R means that it's like right associative?
Yes, right associative precedence, that's right. So you have possibilities of having infix R for right associative operators, they group to the right, infix L for left associative, and just infix on its own where you don't specify how you associate, which means you'd have to put in brackets if you use the operator multiple times. Yeah.
If instead of bar plus bar you do bar x bar, it doesn't like it. So what's the reason for that?
So the rules, the syntax for operators, for infix operators, is that they have to be built from a particular collection of symbols only. So you can't mix symbols and characters. And the same goes for function names. Function names can only contain basic alphanumeric characters plus underscore, and yeah, so very, very limited rules. I don't remember the exact rules, but yeah, that's the reason. So there's some symbols you can't use and some that you can. I don't remember the exact rules, but we can look that up if you're interested. Okay. We've talked about components of a playing card. We haven't got very far yet. We talked about a rank and a suit. The rank was a bit more interesting because one of the constructors of rank contains some extra information. That's nice. Now we want to define a card which combines a rank and a suit. So let's define this also as a new data type. So we could model a card as just a pair of a rank and a suit, right? That's one way of doing it, but if we model it as a new data type, then we can't mix up the pair that we use to represent a card with any other kind of pair. And that sometimes can be useful to have a unique representation. So we'll do that here. It's not going to be an enumeration type because there won't be any choices. All cards look the same. They consist of a rank and a suit. So they're going to contain a rank and a suit, but this wouldn't form a definition. We need a constructor, so I'm going to use the constructor card. So that's the definition that I'm going to use. Now this looks a little bit odd here. This card on the left of the equation is introducing a new type, a type of cards, and I'm doing what is typically done in Haskell, that is to use the same name as the type for the name of the constructor. So the thing on the right here is a constructor, lives in the expression world, different worlds. That's why I can get away with using the same name. We never confuse types and expressions. Okay? But this is the thing you can think of as telling us that we're building something in this data type. Okay? Let's derive show and EQ. Now I hesitated for a second there. Does it make sense to test for equality on cards? Well, in some card games it shouldn't do, because each card should be unique. So you shouldn't be comparing, but you might want to check whether somebody's cheating. You might want to check whether your code has bugs, or you might be in a card game involving multiple packs of cards. So it's maybe okay to have an equality operation. Certainly be useful for testing. So why not? Derive equality. And of course, the derived equality, two cards are equal if they have the equal rank and equal suit, obviously. Okay, any questions about that? It's not compulsory to use the same name here. Okay? If I wanted a long and descriptive data type name, I might just choose a really short constructor name. What's the type of card? It's a function. Good, good, I heard a function. It's a function which takes a rank and a suit and gives us back a card. So when I ask what the type of a card is, this is card as an expression, as a piece of program, not as a type. Oh, it's not in scope, so I better reload that file. Oh, I've got something wrong. What have I got wrong? Ah, yeah, that's good. So I wanted to do equality on cards, but I never talked about equality on suits. So let's add that to suits as well. It does make sense to have equality on suits, absolutely. We're certainly going to compare in many card games whether you've got a heart and I've got a heart. Okay. Let's reload that. Okay, at least it reloads now. Now, where was I? What was I going to do now? Oh, yes, I was looking at the type of a card. It is indeed a function. When you get a rank and a suit, it creates a card for you. So this card is the expression, this card is the type. I'll introduce it early on, even though it's confusing, because it's the common way to write these things when you have a single constructor. Okay. Now, given the definition, it's very natural then, given a card, we'll often want to talk about what's the rank of the card, or what's the suit of the card. So it's very natural then to define selector functions, which given a card will give you back either the rank, if you want the rank, or the suit. So it's natural to define a function rank, taking a card and producing a rank. And how would it work? How do we define it? We use pattern matching. We take a card with a rank R and a suit S, and the rank of that card is just the R. And similarly for suit, with a card R and S equals S. So these are the two selector functions, and in fact we can obey our suggestion from the earlier example. We're not using S in this example, so we don't care what that is, and we're not using R in this example. So that would be a more natural, communicative way of defining rank and suit. Okay. Now it turns out that there is actually a shorthand way of defining the data type and the basic selector functions at the same time. And that is to use this declaration here. Okay? So this syntax is not particularly obvious, but this single line here is equivalent to the 3 lines here. You still have to add the deriving EQ show and so on. Okay? So this is a shorthand way of, at the same time as you define the data type, defining the names of the selector functions. It's handy, it's not essential. I don't think we use it very much during the course. We won't see it so often. Any questions about that? Excellent. Okay, now's a great time to take a break, and after the break we'll look at some slightly more complicated functions.